I'll start it.
Yeah, yeah.
Yeah.
You can put on the webpage, maybe this.
Yeah, we can work it out. You can put it in with the YouTube. Maybe put it to YouTube and put a date space so you can have people.
Yeah, I just wanted to make sure someone, so Ben is the official recorder, which is great. Stop it again, but, that's the end of the end of the morning session.
Yeah.
So, 4 hour.
Yeah, it's not during the break.
Okay. Okay. People are forced now to sit at this big table. Gotta get here early.
Get the bad seats. I need a good seats.
Oh, yeah.
We're already getting obviously, Holly, something else for yes.
Perfect. Coffee's here.
Very quiet.
Okay, let's get started. Our first event here is Holly's going to give a welcome.
So if you turn here, there we go. Yeah, I can see it out. I was trying to figure out a way to address both. Does it follow? Okay, anyway, all right. Cool. Welcome everybody. Coffee just arrived for those of you here in person, and I wanted to first say welcome, but I really wanted to thank everybody for your service in helping us on this UCoMP journey. We're kind of in the stages of growing pains, I would say, but really thank you for helping us work out the bugs. And I hope this is a very interactive and useful event for everybody. What we're working towards is a real community event, hopefully not too distant future. And that way we'll have the data already and we'll have people using it for science. But this is really a great step forward, and we're really grateful for all of the help that you're providing during this event. So thanks for coming in person. Around the world. I don't know everybody here, so for those of you who don't know me, I'm Holly Gilbert. I'm the director for HAO, and I'll be in and out of this meeting, so just ignore me as I'm kind of squatting and then not. We're going to talk about logistics in just a second. One aspect I really wanted to point out, because it's exciting for me, is the amount of engagement that UCoMP has garnered from the early career scientists. I know a lot of you have already been working with them, and it's been really fantastic seeing how engaged and how energized everybody is. So I hope that continues, and you're all part of that. And yeah, I just again wanted to say a quick thanks and hello, and I'll turn it over to Steve Tomczyk.
Thank you, Holly. So I want to introduce Cheryl. Maybe you already know her. She's been the, organizing this and setting everything up. And if you have a hotel reservation, it's because of Cheryl. So I want to just. Thank you, Cheryl.
Welcome everybody to HAO and the UCoMP workshop in Boulder. Just a few quick logistical things. Most important to me anyway, restrooms. There's 2 at the end of the hall this way, and then there's larger ones if you go to the end of the hall that way. They'll be on your left. For those of you visitors who don't have office space here, I made a list here, and each one of you has your own private office if you need to go make a phone call or want some downtime or whatever. On the list here, every day we're going to post the agenda, so feel free to glance at that. If anybody would like soft drinks, there's a limited amount in the fridge just outside the door to the left, including root beer. Lunch will be served on the 2nd floor cafeteria. So you go down 1 level and it's to the west. Okay, and you can eat it up there, or you can go outside underneath and eat. Vegetarian meals I ordered specifically for those who requested them. So if you did not, please do not take one. Let's see, today and tomorrow, Tuesday, Wednesday, there's a meeting downstairs, so you will be able to get in the door. Thursday, Friday, that meeting is not happening, so please arrange with a staff member or coordinate somehow to get yourselves in the morning. At the end of the week, please recycle your name badges. There's a box in the back of the room. There's also some hand sanitizer and masks I left for you. And lastly, if we're sponsoring any or all of your travel, please send me your receipts when you go home during the week, whatever. Thank you very much. You can reach me if you have any questions. I'm happy to help. I'll be here in and out during the week. And over to Steve.
Thank you very much. So I thought we might just start with some introductions, maybe go around the room and also go around to our remote participants to just very briefly, if you could, just introduce yourself, say who you are and like where you're at or what you do. And I'm going to start with Mike Galloy over there. We're going to go around the outside and then the inside here. Please go ahead, Mike.
I'm Mike Galloy. I work here. I do the software development. So I wrote the calculation pipeline for
I'm Julia Madekova, I'm a scientist here at HAO, and I work with the environmental.
I'm Jenna Samra. I'm an instrumentation person over at the Harvesting Study Center for Astrophysics. And I'm working on some instruments that I hope will be complementary to UCoMP.
Hi, I'm Anna Wisniewska. I work at the EIP in Germany, and mainly I do hydroseismology, but also ground-based observations.
I'm Ursula Wąsieślicka. I work at the University of Wrocław in Poland, and I work with Sarah, with comp data, and now with UCoMP data.
I'm Judith Santa from University of Michigan, and I do MHD modeling with the emphasis of synthetic observables.
Hey, I'm Alan. In this context, I'm doing vector coronal magnetic fields.
Hi, I'm Daniela Bush. I am a scientist here, and I'm mostly interested in what the chromosphere relates to the corona.
Hi, I'm Maurice Wilson. I'm a postdoctoral fellow here, and in general, I work on CMEs and describing why their energy builds up and releases.
I'm Ben Berkey. I'm the Monolith facility manager, and I wrote the real-time software for UCoMP.
Gabriel Dima, I work in series and NOAA, and I work on the white light coronavirus. I basically write pipelines now.
I'm Matthias Remper. I work here and I mostly do radiation MHD modeling of the solar atmosphere. So I would be interested in using these simulations to actually forward model UCoMP observations. So if anybody of you is interested in looking at simulations. Yeah.
I'm going to introduce myself.
I'm Sarah Gibson. I'm here at HAO, and this week I'll mostly be focusing on the forward modeling, the forward codes, and working with you guys with that for accessing and comparing UCoMP data to models and other data.
I'm Joan Burpel. I'm the manager of Mauna Loa, and here I have the white light chronograph, and I study CMEs and work with the team.
I'm Paul Bryans. I'm here at HAO too. I'm mostly do spectroscopy of the chromosphere and corona, but I've never used UCoMP data before.
Hi, I'm Mo Moller. I'm a postdoc here at HAO, and I'm interested in 1030 observations from UCoMP.
Hi, I'm Inge from University of Michigan. I'm a fifth-year graduate student, and I mainly work on UV spectroscopy using Hinode and Soho Super.
Hi, everyone. I'm Zihao Yang. I'm a PhD student from Peking University in China, but I'm also visiting here as a local fellow. I'm mainly working on UCoMP wave observations on the corona magnetic field environment.
And I'm Steve Tomczyk. I am a scientist here at NCAR. I'm the PI of the COMP instrument, and I just want to say I appreciate, I'll add to Holly's appreciation for everyone who's here and is interested in UCoMP, and we want to really help you to be able to use the data and utilize it to do your science. So Samaya, a great idea about the tables. You see everyone sitting around the outside of the room at the table. So good job.
Steve, do you want to have the folks online introduce themselves? The folks online.
Yes, we're going to go around. So let's start. I'm going to just read some names, and if you and go through the list of online people. But Ambika, can you introduce yourself, please?
Hello, my name is Ambika Saxena, and I'm a PhD student at ADS Nainital, India. And my research interests include mass and energy transfer among different layers of solar atmosphere. And I'm very happy to be part of this workshop. Thank you.
Thank you. I see Jyoti Shurin next, but I also see Dipankar and other people in the room. So please go around your table and introduce yourself. Thank you.
Yeah, thank you, Steve. So this is Dipankar Banerjee from Aryabhatta Institute. I've been involved with the spectroscopy. Really was nice to see Sumer name again, Sumer CDSIs, whatever you'd call it. But more recently, we have been involved with the Aditya mission. And just a quick update, Aditya is going to be launched on 2nd September, this Saturday, in the morning time of Indian time. So we are looking forward for joint observation from Aditya, because Aditya has an inner coronagraph with a similar field of view. So it will be fantastic to have joint observation and science with the UCoMP and Aditya's coronagraph. So we have students here. We have started looking at the COM data. I will request them to introduce themselves. Yeah.
Hello everyone, I am Jyoti Soran and I am working with Professor Dipankar Banerjee. I study coronal mass ejection and their thermal properties using COMP and UCoMP data. So yeah.
Hi everyone, I'm Upasna Baveja and I'm a research scholar at Aries. And I work mainly in the coronal seismology, and I have worked with UCoMP data, COMP data, and would like to work with UCoMP data further.
Mark Connor? Oh no, is there someone else in your room? I think I see.
Yeah, so there is one more student. He's just come in. Arpit, yeah, maybe Arpit, you can introduce yourself. Yeah.
Yes.
Hi everyone, I am Arpit Kumar Shrivastava. I have worked on oscillations in small scale coronal loops using UI data, and I'm interested in using UCoMP and COMP data. So that's why I'm attending this workshop.
Wonderful. Okay, Mark Cotter.
My name is Mark Cotter, and I work at the Mauna Loa Solar Observatory as a scientist in Hawaii, and I operate the instrument.
Don Kolinsky.
Everybody, I'm from HAO. I developed the UCoMP website, and we'll be adding more more data as soon as it becomes available.
Thank you. Shahida.
Hi, can you guys hear me clearly? I'm on mic and mute, so please don't mind my background noise. I'm a postdoctoral research fellow from US Naval Research Laboratory, working with Mark Linton and Robin Colino, and from the teams of Parker Solar Probe and Solar Orbiter. I work on coronal mass ejections and solar flares. I use white light data and also radio observations from Expanded Owens Valley Solar Array and other instruments. Yeah, I'm super excited to be here to use UCoMP data. And I have a talk at 11:10 MDT, so please, I will talk more about my work during my discussion.
Excellent.
Thank you. Thank you.
Richard Morton.
Hi everyone. I'm Richard Morton. I'm from Northumbria University. I'm joining all the way from the UK. I've got a company as well. I actually work on waves, and I've used COMP and UCoMP in the past to do some wave studies. And this is Benjamin, and he'll be looking forward to working on Cosmo when it's built.
Is it me, or do the students seem to be getting younger? Maybe I'm just getting older. Ravina?
Hi, I am a visiting student at HAO, visiting as a NUCAC fellow, and I work on the forward modeling of coronal emission lines in the extreme ultraviolet, and I also work on the design of spectropolarimeter.
Excellent. You're sitting down the hallway from us now, yes?
No, I'm sitting in my room now.
Krishna? Might be muted, or maybe you've gone away for a moment. Okay.
Yes. Hello. Hello. Hi. I'm Krishna Prasad. I have recently joined as a faculty at in India at Aries. So I work mostly on MHD waves and oscillations. I have used some COMP data before, but I haven't started using UCoMP. Yes, but I have used these lines from a ground-based coronagraph data, Norikura coronagraph.
Excellent.
Thanks.
So thank you, everyone, for introducing yourselves. And I think now we can move on with the first tutorial, which is me. So let me see if I can set this up. And is there anything else? Anyone has any questions or anything? Okay, so I screen show's presentation. Look at that. How do I do that?
It does. Share Google.
What's that? I have to share.
Yeah,
Well,
you go
no.
to the meeting and
You can just try clicking.
Yeah.
And we're here.
It's just a full screen.
Oh, I know. Yeah, so you have to exit, go back in and do full it off.
Stop. Sorry, everyone. So,
You'll all probably have the same issue you're sharing, so it's usually better just to show full screen sounds if you're doing it PowerPoint. Otherwise, yeah, so select entire screen. And select that.
Someone please admit. Thanks, Ben.
Thank you.
That should work.
Okay.
Okay.
Very good. So, hi, everyone. I'm Steve Tomczyk, and I'm going to talk about the UCoMP instrument. I'm going to try to talk about aspects of the instrument that are practical. In other words, that you might have to think about when you're using the data. And you'll see what I mean by that as the talk goes on. So the UCoMP instrument is an upgrade of the COMP instrument. I know it goes without saying, but it's an imaging spectrometer with a polarimeter. So it's an imaging spectropolarimeter. The proposal for UCoMP to upgrade the COMP to UCoMP was led by Enrico Landi of University of Michigan, and I'm happy to see several University of Michigan people here. Our goal in upgrading the COMP was to increase the wavelength coverage, the field of view, and the spatial resolution. The first light was in May of 26th of 2021 with UCoMP, although the first data we took wasn't usable, and eventually we worked out some of the kinks. We're still working out kinks, as Holly mentioned, and hopefully all of you will see lots of data during this workshop. So the UCoMP, we think, is a prototype for the filtergraph instrument that we hope to put behind a Cosmo large coronagraph, a 1.5 meter aperture coronagraph. So it's a narrowband filter instrument, and we can tune the passband of the filter electro-optically. So the lines that initially we are observing with UCoMP, you can see the list right here. I won't read through it, but you can see there's iron 10, 11, 13, 14, 15. There's a line pair of iron 13 lines, which serve as a density diagnostic. There's H alpha, and there's thank you, helium 10A30 for us. So H alpha and helium 10A30. So I show here the temperature ranges, and the filter, the narrowness of the filter is in the rightmost column. It's my cursor shows up. In the rightmost column is the bandpass of the filter in nanometers. So the filter gets narrower as you go towards blue wavelengths. I'll talk about that again. So the increase of field of view on the left is the COMP, original COMP field of view. We had one detector and we had two beams. That is, both instruments are designed to observe corona and background continuum simultaneously. The COMP had about a 0.38 solar radius field of view. And there was one camera that shared both beams, and it had 4.5 arc seconds per pixel. The UCoMP, we have two detectors that are formatted as you can see on the right. We have about 3 arc seconds per pixel, and we have a full 1 solar radius field of view towards the east and the west, less towards north and south, and a little bit more in the corners of the detectors, you can see. So this is a more of a Cosmo-like field of view, and that was one of the reasons for doing this. 3 arc seconds per pixel now. So here is a diagram of the optical system. The coronagraph has a 20 centimeter objective lens. There's a diffuser that we can insert in front of the objective for us to do calibrations. I'll talk about what kind those are. And there's an instrument box at the back where everything pretty much happens back there. And that instrument box is sort of has a larger view towards the bottom of this figure. You can see there's an occulter that can be moved around and completely out of the field of view. There are polarization optics that can be inserted. Polarization optics can be inserted. Polarization optics can be inserted into the beam. There's a Leo stop, which blocks the diffracted light from the objective. There's a polarimeter that gives us full Stokes IQ UV. There's a filter wheel that selects one of those 9 wavelength regions. The Leo filter, and I'll talk about a lot of these things in more detail. The Leo filter is this electro-optically tuned narrowband filter that allows us to tune across these emission lines. And there is a beam splitter and 2 detectors at the back. And this is what gives us the continuum plus coronal band passes that allow us to observe those simultaneously. And that's important to remove things like aerosols that float through the field of view for our ground-based observations. Here's a couple of pictures. The UCoMP in the lab is on the left, and on the spar at Mauna Loa is to the right. Maybe that's the comp and not the UCoMP. That's definitely comp. That's definitely comp. It's got the blue dome inside, but it's the same enclosure and the same box. So that's what it looks like next to K-Core on the spar at Mauna Loa. Mauna Loa, maybe you all know, but our road was covered with lava late last year, and we have been closed since then, and we hope to get back online maybe April of next year. So we have plenty of UCoMP data, good thing in the can, but getting new data, we'll have to wait until the spring. So just a little more detail, the UCoMP tunable Leo filter is shown here. It's a 5-stage birefringent filter. And on the bottom, you can see sort of 6 tunings in the area around iron 13-1074. And basically by changing voltages, you see all these wires coming out of the filter. And they're there to drive liquid crystals and allow us to tune electro-optically the bandpass of that filter across the lines, as you see on the lower left. It takes us about 300 milliseconds just to tune every time, because the liquid crystals have to settle. These are pneumatic liquid crystals. So that's something to bear in mind as a practical point. There's temperature sensors, which correspond to some of those wires coming out of the thing. And there's 27 optical elements that comprise this thing. There are lithium niobate crystals and liquid crystals and retarders and polarizers. And so it's quite a complex thing, but it works. And it has a 50 millimeter clear aperture. For Cosmo, we think we're going to need something with about twice the clear aperture. But we'll use lithium niobate crystals for Cosmo. That was one of the reasons for doing it here. And by the way, people feel free to ask questions. If you're remote, raise your hand button, and here people could just raise your hand or yell out. But please feel free to interrupt, because this is a workshop. This isn't a conference where This is intended to be very
Can I ask a question then?
interactive. Yes.
What is the difference between the filter wheel with the wavelength selection and the Leo filter?
The field of view.
You said you had a filter wheel
The
to change
pre-filter.
wavelengths, but you also have the Leo filter. What's the
difference
need for
is
both
that
of them?
this next slide might answer your question. That the Leo filter itself has a periodic transmission structure, like a fabric row, you could think. So to select one of these, and this goes over the whole spectrum, to select one of these, say at 1074, we insert one of the pre-filters. Look at the middle plot there. And then the bottom plot is what we then observe, what goes to the cameras. So go ahead, Richard.
Yeah, I was just, you said that you had temperature sensors on the filter, and I guess that made me think, is there some uncertainty on the wavelength positions due to temperature, or is it kind of negligible and you don't really worry about it?
If the temperature of the calcite change, the lithium niobate crystals change, it will shift the filter. So we do two things. One is we stabilize the temperature of the filter within maybe 1/100th of a degree centigrade. And we also though measure the temperature, and then we compensate the voltages that we use to drive the liquid crystals to compensate for any temperature drift that is left. So we do take care of temperature issues in the filter. Now, Paul was asking about, so I don't know if I answered your question.
Yeah, you
so
did.
the pre-filters select which one of those orders of the Leo filter. We observe, we have, excuse me, 9 filters in our filter wheel. So we can select out 9 different emission lines to observe. If we had more filters in our filter wheel, we could observe some other lines as well. Yeah.
Can you say something about the choice of the lithium niobate? What are the advantages compared to more traditional niobate for the calcite?
Yeah, that's a good question. Traditionally, people have used calcite crystals. You need a birefringent crystal to make these Leo filters. Traditionally, people have used calcite. Now, calcite, people don't know how to grow calcite, so it's basically dug out of the ground. So it limits the quality and the size of the crystals that are available. And as people have mined it over the years, there's less and less calcite available. Lithium niobate has half the birefringence of calcite, so you need to have twice as thick crystals to do the same thing, which is fine. But people can grow it in very large sizes in you know a laboratory environment. So if you want to have a large filter, which you need to couple to a large telescope like the Cosmo Large Coronagraph, you need large crystals, and that's why we shifted from calcite we've used in the past to lithium niobate to have larger crystals. Go ahead, Upasna.
I think it's just they're just joining.
Oh, they're just joining. I'm sorry. Okay, so that's what forced us to go to lithium niobate. Lithium niobate is a little more temperature sensitive than calcite, and that's why we've taken great care to stabilize the temperature of the filter, to stabilize the enclosure, that back end of the instrument as well. So we have 2 levels of temperature control, and then we have also temperature compensation by measuring the temperatures, changing the voltages on the liquid crystals. So we talked about that there's 2 beams for UCoMP. And if you look at the top, you can see sort of an example of the tunings where the central transmission peak, this is not the coronal emission line. Coronal emission line is a little bit wider than that transmission peak there. So there's a transmission peak like the black line in the top figure, and the 2 side bands there, that is a transmission of what goes to the other camera. So camera 1 gets the transmitted light through that black band pass, and the green band passes go to camera. So one's camera 0 and the other's camera 1, as we call them. And we can swap those. We can make camera 0 be the continuum and camera 1 be the corona as well. Now, by changing the liquid crystals, we can also favor one of those band passes. Sort of in the middle, we can basically put the continuum channel mostly to the blue of the coronal channel. And also we have a red tuning where we can put the continuum band to the red of the coronal band. And these are to avoid, you know, other emission lines nearby or caloric absorption lines through the Earth's atmosphere.
Just to be clear, your continuum gets overlapped, the two get overlapped in one camera. They're not separable anymore once they arrive at the camera. Or there's just two cameras, not three.
There's two cameras, so one of them gets the coronal band and the other gets the continuum band.
Both sides of the
Yes.
camera. Okay.
Both sides,
Yeah, that's
exactly.
what I was
And say that both sides go to the
Okay.
same camera. So it sort of, yeah.
Okay.
It actually is, it turns out to be a reasonable thing.
Yeah, no, that makes sense.
Anything else that you?
No, I just said yes.
And like I said, these are all selected with those liquid crystals that are in the LEO filter, all these tuning bands. And as I said, we can swap them. So we can put the coronal on camera 0 and the corona on camera 1 and the continuum on camera 0. And that helps to reduce systematic errors by beam swapping, so to speak. So here's one of the cautionary things I wanted to talk about. So now I'm showing the same as that top figure in the last slide, but in a logarithmic plot. And why am I doing that? What I'm trying to show is 10798, which is at the center here. But 10830 is not very far away. You can see here. Now, again, so this is the LEO filter transmission. This is the pre-filter transmission, also shown in log. And then on the bottom is the product of that, what we actually observe. And you can see that these side lobes, these band passes out here, are greatly reduced. However, if we tune 10798, like, you know, electro-optically, just tune the LEO filter a half a nanometer to the blue, what happens is you can see that this continuum sideband, the next order, corresponds to 10830. Now, why is that a big deal? You can see that it's 3 orders of magnitude lower than the main order that we're observing. Well, 10830, it turns out, is like 1,000, 10,000 times brighter than iron 13. So you have to be very careful what happens with your side lobes. These interference filters only, you know, have just some certain kind of fall off, which has some finite transmission, which isn't usually a problem, except when you're right next to 10830. And so we do see some artifacts in 107.9 data due to 10830 going through some of our next order side lobes, I would call that. Another thing is that the 706 line has a prominence, a weak prominence line close to it, such that, say, the continuum channel, you know, as we tune these all tune together, and you can tune your continuum channel into that prominence line that is next to the 706 emission line. So one has to be aware of these and wary of these, and Maurice knows about these, and he'll probably talk about those later on. Is that someone joining, or is that
Yeah, everything knows the join.
Okay, thank you. So just moving on a little bit here, as I said, there's a diffuser that we can put in front of the objective, and this does several important things. One is it gives us a flat illumination that we can use to correct pixel-to-pixel variations, the so-called flat field calibration. It allows us to normalize the coronal images to the solar disk center intensity, because we've measured how bright this diffuser looks when it's illuminated by the sun relative to the sun intensity. So it gives us a radiometric calibration of how bright the corona is. So it allows us to normalize the transmission of all these tunings of the LEO filter and the continuum channels. And the two beams, it allows us to normalize those transmissions as well. So it's a very important for normalizing the transmission of various things and the sensitivity. So it's extremely important. And every hour or two, we stop what we're doing and we put the diffuser in front of the telescope and take data with the diffuser to perform these calibrations. So the polarimeter. So we have a polarimeter. I'll go back quickly. So the polarimeter is here. And it measures the complete Stokes vector of the image. How does it do that? Well, it contains two ferroelectric liquid crystals in it. These are different than the liquid crystals that are in the LEO filter. These are much faster, and these are just two states. It's like a retarder that you could rotate to two angles, and there's two of them. So we have four states that this polarimeter has. And what happens is by rotating these, effectively rotating retarders electro-optically, and then we have a polarizer, it changes the intensity coming through that unit according to the polarization state. So it encodes polarization state by the modulation of the intensity at these four states of these ferroelectric liquid crystals. They're very fast. So we can modulate polarization much faster than we can move in wavelength. And we do that. We go through a lot of polarization states to build up signal to noise, and then we move the wavelength states. And Ben will talk more about how we observe that. And now it's designed to be very efficient. This is a so-called polychromatic modulator, polychromatic polarimeter. It gives us high efficiency from 500 to 1100 nanometers. You can see the efficiency plotted on the right. That they're really quite good. Let's go to the next one. So we have to calibrate that polarimeter. And what we do is every day, at least once a day, is we move in, these are the optics here circled in this orange circle. We move them into the beam. The beam is the red line. And we rotate them at various angles to create some Stokes eigenstates into the modulator. And the modulator is this thing all the way at the right here. And obviously your calibration optics is in front of your modulator. And so by putting those eigenstates into the modulator, we can calibrate that transformation matrix, so-called demodulation matrix, that transforms those four intensities into Stokes I, Q, U, and V. And as I said, it's very efficient over the 500 to 1100 nanometer range, but the demodulation matrices are much different depending on wavelength. So it's sort of a different polarimeter at each emission line we observe, but it's very efficient at all the wavelength regions. So and that's all pretty well worked out. You can see here, I'll just mention the this is the occulter here. It's right now it's out of the beam. So we move typically when we're observing the corona, this occulting disk gets moved into the beam, and we can move it to block out the solar disk. And during our calibrations, we move the occulting disk completely out of the beam. So the detectors that we have are indium gallium arsenide, 1280 by 1024 detectors. They have a lot of sensitivity out near 1 micron at our wonderful iron 13 lines. However, in gas, and this is thinned in gas, this is in gas that has been made to be more sensitive at shorter wavelengths, but you can see it's not tremendously sensitive at 530 nanometers here. much less sensitive than it is at, say, 1024, like a factor of 5. So our quantum efficiency is much lower at shorter wavelengths, and this causes us to have difficulty measuring iron 14530. The LEO filter band passes are also narrower. If you remember that slide I showed with all the lines. And so getting photons through the LEO filter and detected by the camera is much more difficult at 530 nanometers. It just is, but that's a trade-off we made early on in the process that we prioritized 1074, 1079 over iron 530 nanometers.
Plus the sky is brighter and scattering's higher. Plus the sky is brighter and scattering's higher. Everything.
Yeah, that's right. Everything is better in the infrared. It's just that the instrumental scattering is lower, the sky scattering is lower. So everything is favored in this instrument for longer wavelengths. So I'm done talking about the instrument. I just wanted to talk about what we can get from the instrument. I have a little time left, right? The agenda. Someone has it pulled up, I'm sure. 15 minutes, and I won't even take that, I don't think. So what can we do with this data? Most of you know more about this than I do, but plasma temperature and density can be derived from intensity ratios. The line of sight field strength we can get from circular polarization, that is Stokes V. However, it's very insensitive. For these lines, like iron 13-1074, which is the most sensitive line probably we have, you get Stokes V over Stokes I. It's the circular polarization over intensity, 10 to the minus 4 per Gauss. So if you want to measure 1 Gauss magnetic fields, you need a signal to noise ratio of 10 to the 4. And that's very difficult to achieve for a telescope which only has a 20 centimeter aperture, I should say. From linear polarization, which is much easier to measure, the linear polarization signals are 5 to 20%. So that is Stokes Q and Stokes U. We can do a lot better there. And people will be talking about this today. And that's important because that tells us the direction in the plane of the sky of the magnetic field. Not the strength in the plane of the sky, just the direction in the plane of the sky. Now, we can, by tuning across an emission line and watching a Doppler shift, we can measure the line of sight velocity from the Doppler effect. And that's an intensity. So that's high signal to noise because that's just intensity. And why is that important? The Doppler, one reason it's very important, and people will talk about this, like see how, is that we see Alfvénic waves in velocity, oscillating in velocity. The corona is just filled with waves, and they show up much stronger in velocity than in intensity. And so we can perform coronal seismology by measuring the phase speeds of these waves, which can be related to the plane of sky direction of the magnetic field. So if you were able to measure the line of sight strength of the magnetic field through Stokes V, Zeeman effect, and as well as the plane of sky from a coronal seismology, you would have the vector magnetic field of the corona. And that is a big goal of ours moving forward, especially with telescopes like Cosmo and things like DKIST, large aperture telescopes. So just quickly to show some data prompts.
Question.
Oh, sorry.
Sorry, a quick question. What stops you from just integrating for a really long time and trying to get Stokes V, modular the rotation of the sun and everything? Like what's your fund? I understand that you have a small aperture and you have low sensitivity and it's a challenging measurement, but I guess
is it possible with something like UCoMP if you integrated for very long periods of time, and corona had a geometry where it wasn't changing a lot, you might be able to do something. The way I say it is that we can't routinely measure the line of sight component of the magnetic field with a telescope as small as UCoMP.
Okay.
We're hoping that if we really average a lot and really beat down the systematic errors, that we'll maybe be able to see some Stokes V signals above the noise in certain parts of the corona on certain days.
Okay.
And that's something that we're gonna work on. And I encourage other people, if you're interested in that, to pick that up.
I don't know if Joan or Ben want to comment, 'cause we started playing around with this.
Yeah, we did.
Oh, okay.
Yeah, we looked at some active regions that were strong
Mhm.
with sunspots near the limb. We're a little bit limited because we had started observing with 3 wavelengths only for some period of time. We needed 5. Oh, there's a hint,
Okay.
but I wouldn't write a paper about it.
Yeah.
We need to integrate longer. And you're looking at having to average like 2x2s at least.
Yeah.
And it's a hint, it's a small number of pixels. So it's enticing. but
It's
we
not
need
just
more.
a slow rotation, we're also limited by something from the ground. So at some point that's very seeing, I mean, you cannot integrate 10 hours and add them all up. So maybe days when the scene is very good, starting early in the morning. So if you have the right condition in terms of atmospheric scene and an active region, and that would be the time maybe to run the spatial program to target V with 5 points. And we can talk about maybe at the end of the workshop, what are the observing program that we can think of going forward. Okay. They can target specific science goals.
And we also had short exposures, and we want to precisely align the images then. Which, because the sun is drifting under the occult a little bit. So,
And the other thing so far, we've not optimized our observing program at all.
Yeah.
We came up with something that was an engineering thing until we ran through enough data and understood what we're doing. So it is completely just me going like, I don't know, we need some of that, some of that, some of that. That makes the whole day.
We have a sort of a general observing program. If you really wanted to try to measure line of sight magnetic fields, you'd probably just observe iron 13, 1074 all day.
Yeah.
And stop observing 637 and stop observing this or that or any other thing.
Yeah.
And concentrate on it. We can have a campaign to do that. Maybe a campaign when your payload is flying. And so, talk about it and optimized, we have a very generalized kind of observing program right now, which tries to do everything.
Yeah.
So it's hard to do something really well. So.
Okay, so there's something fundamental. I guess that I get that you wouldn't be able to do it yet necessarily, but it sounds like maybe something.
Yeah.
Yeah.
I think we could do it with the right conditions to do that.
Okay.
It's just difficult because we cannot just integrate.
Yeah.
Time pointing and seeing at some point.
Yeah.
So, yeah, I was going to comment that I want to make sure people understand that this is not something that we're going to go away and do. I mean, it's not something that we have to do. Part of the reason you all are here is because we're trying to introduce to you to the data that is possible. And if any of you are like, you know what, I would love to work on a project to get Stokes V from UCoMP data, we want you to come up and tell us that, because that will be the catalyst to make this happen. So, we can't do everything. We don't want to do everything. We want you guys to write a science paper on this, right? So on Friday, we'll talk a little bit more about observing plans and everything, but think about this as you guys are empowered to take a aspect of UCoMP that you think this from learning this week sounds like it would be a cool thing to do, and just say, I'd like to do that, and we will support you. That's our role.
So we are very open to a campaign and special observing plan. I mean, we were in the commissioning phase before the action interrupted the observations. So we didn't really have that open to that, but we have been to there several times. Maybe we can have a Monday meeting when we plan observation for the rest of the week based on what people have requested, a little bit like they do on the satellite.
Yeah.
And this one is really from the ground because it's much easier to change observing program. So you can tell you that they are there and need to say, oh, there is something that really is interesting. I should run my CME program. They can do it basically on the fly. You don't need to upload comments. So there is in advance like with the satellite. So there is a lot of flexibility that we can play with for sure.
Yeah. So that's all absolutely true. But we also want to maintain synoptic observations every day. What we have been doing, and maybe Ben or someone's going to talk about what our observing program has been, but to get that coronal seismology, we have to observe 1074 at a 30-second cadence for about an hour in order to perform coronal seismology. See how we'll talk about the coronal seismology, and Ben will talk about the observing program, like what will we do now? And if people have ideas about what you would like to do for a campaign, we can talk about that. So this is just showing some data. This is iron 13-1074. There's Stokes I. Go ahead, Richard.
Sorry, it's just before you move on. So you were talking about on the previous slide, it's got the signal in Q over I and U over I. You said you need 5 to 20% signal to noise level. Is that what that's telling me?
I guess I'm saying those signals, depending on the height in the corona and the line, those signals can be like 5 to 20%. That much larger than 10 to the minus 4. In other words, that it's much easier to measure linear polarization in the corona than circular polarization.
And how well is COMP measuring it then? Do you have a sort of idea of the signal to noise?
Much better than 5 to 20%. I don't know, probably a few tenths of a percent.
Okay, great, thanks.
It depends, in how long and which line. I mean, 637 doesn't have any linear polarization. It's identically zero according to the atomic physics. So, well, look at this and tell me how well are we measuring it. There's Stokes Q over I. And you can see the color scale. So this is the fraction Q over I plus minus 20% for Q and U. And you can see the signal to noise looks pretty good there. Now the magnetic field is mostly radial, and that's why you see sort of the color table rotate around in these pictures, because the magnetic field is mostly radial. The all the way to the right is Q squared plus U squared square root over I. That is the percent of linear polarization. That's in some kind of a log scale there to bring out the figures, the features there that people will talk about also later in the workshop. Line of sight velocity, you can see. Line width, azimuth. That is the azimuth, again, is the direction of the magnetic field in the plane of the sky. You see that color bar coming around. That's because the magnetic field is mostly radial. But what shows the departures from radiality is when we plot that magnetic azimuth relative to the radial angle. So that lower right figure shows the angle with respect to the radial of the magnetic field of the corona. You can see there's all kinds of stuff going on there. So yeah, it's mostly radial kind of, but it's really not in detail radial. And there's so much information that is rich with information there on the magnetic field of the corona.
I have a question about that, Steve. To do that, you need to know where the center of the sun is, right? So how well do you know that?
Yeah, I mean, the sun is behind the occulter, so we don't know exactly where the sun is. So that's sort of with respect to the center of the occulting disk. And we count on the observers to kind of keep the sun behind the occulting disk.
How do you do that? Like, how do you practically measure it? Do you take the occulting disk out of the way and put a filter in or something?
No, I mean, when the sun starts to peek out from the occulter, we move the occulter.
Okay. Well, maybe I missed this at the start, but what's the size of the occulting disk?
The lower limit of the occulter is about 1.03, 05. It changes with time of year. The Earth gets closer and further from the sun, so the apparent size of the sun changes. We have to change out those occulters several times during the course of the year. So it changes a little bit, but it's of order 0.04 solar radii, something like that.
We had a question, yeah. Shahida.
Go ahead, Shahida.
Steve, I have a quick question. On the boundary of each of those maps is irregular, right? So what defines that? How is it done?
Like the outer boundary for that, for these?
Yeah.
That's a good question. At some point, we kind of deem this, the corona, of course, is getting fainter as you go to higher heights. And at some point, it gets into the noise. And for these images, we've sort of set a threshold that the data is not reliable above some threshold. And you're sort of seeing the threshold. Now, in the FITS files, that threshold has not been applied. So you'll see the noisy data out above here, but for the purposes of, well, graphics, we've kind of, we set a threshold for what looks good.
Okay.
If the level 2 is masked and fits, the level 2 is masked
The
and
level
fits.
1, we don't mask anything, so you can see
Right.
all the signal under the filter at the edge of the field of view, when the noise basically dominates. For the level 2 problem, there is some masking applied for a practical reason, and we'll discuss that, I think, in quite a bit of detail during the workshop. And the reason is that actual limitation, for example, when we fit a Gaussian, we cannot really do it. If there is a pixel that for some reason was negative, the noise is so low, when you subtract the background of the continuum, you get sometimes very close to of negative values. Those are basically fixable by noise, and there is nothing you can do for those. So there are some practical reasons to mask. There's some flexibility how much we can mask and how far we can go. So this is something that's really fascinating. The tutorial look at that, how it's done. And it's possible we'll be able to create a product where the mask is separate from data so that if it'll be applied. That's a possibility. I'm a little reluctant because let's talk about that. We'll talk about different.
Yeah.
But there are some
Maybe not now.
Maybe not now. Yeah, we'll talk about that.
So was there another question that I see?
Yeah.
Steve, I have one more question. So do you think that depending on the activity of the sun, the threshold changes, right? Obviously.
Yeah, and I mean, for instance, like Maurice Wilson has to analyzing data to remove these thresholds because he wants to see a CME propagate out to the edge of the field of view and things like that. So we hope to accommodate people who want to not have these thresholds applied to the data, so that they can, we're so yeah, we'll
And this is shown in the level 2 when there is something done to the data, like if we are trying to extract your new to the Gaussian to the line profile, but it's absolutely no masking whatsoever in the level 1. So if people want to go back to the level 1, they will be made available. Well, everything is there.
These are daily averages. These are averages of all the 10.7.4 data on that day. And on the next slide, I'm going to show this quick. This is a movie showing daily averages for like a 1 month period or a 6 week period. And you can see how these things vary with time.
Right.
So since I'm in charge of the time, I'm going to limit myself. But yeah, please,
Yes.
Judith.
So you said that you normalize your intensity to the disk, no? So you normalize each wavelength differently.
Correct.
So how come that the line width not changes with the normalizing? So is the line width from the unnormalized intensity or it's from the normalized?
The line width is from the
So basically,
normalized
calculate-
intensity.
So we take several points across the line. Typically, there are 3 or 5 tunes, and then we fit a Gaussian for that. And this is what determines the line.
Isn't it changing your line width compared to the non-normalized intensity?
So we don't do any normalization of that level. So they are just in relative units.
So you just don't publish the non-normalized. data.
Well,
But
part of the level 1 processing is to normalize to the disk center units. So we don't ever
yeah.
work in units of not normalized.
Everything is in relative units. Sorry, I thought you were talking about dividing Q and U by I. So yes, everything is relative because we are up from the ground. So we cannot make absolute.
Right, because we have variable extinction of the atmosphere. So we don't know what's above the atmosphere. So we just normalize to the sun that we see, which also the disk goes through the same atmosphere. So that's why we normalize.
I understand, but so your line width doesn't change because
It changes with the emission lines. The cooler lines have lower line widths if you look at
You can
them.
see it's a function of position across
yes,
the
but I mean that due to the normalization doesn't change the line.
We don't know because we only normalize the data, ever. We don't have any unnormalized data that we analyze.
When you say normalized, I think it is a photometric calibration. You're putting in things in units of the brightness
But
of the
if you
sun.
have
and then from
like an
there-
emission line and you measure the line width and then you divide that emission line by a factor of 2,
Right.
full width half max should be the same.
Very
So quickly, so we also, as I said, see these alphanic waves. You can see them running around corona all over the place. People will talk about this, especially HAO. And got to cut myself off here. I just, as I said earlier, that the alphane speed can be related to the magnetic field. And since the speeds we measure are in the plane of the sky, the magnetic field is the plane of sky component of the magnetic field that we measure. Still, HAO is thunder here, but this is a map from him on the right showing the plane of sky, strength of the magnetic field. You can see that February 24th, 2022. So to summarize, this 20 centimeter chronograph does have difficulty measuring the Zeeman effect, the line of sight, magnetic field directly. Hopefully, and like I said, routinely, I don't think we can measure it, but we may be able to squeeze it out on certain days where the field is strong. We're going to have to wait for DKIST and Cosmo, I think, to really measure those routinely. But we can learn a lot from that plane of sky direction, the plane of sky strength of the magnetic field, and the degree of linear polarization through the Van Vleck effect. So last thing, I just want to say, the goal of this workshop is to help you users, all of you, to exploit this UCoMP data to advance your science. Please be interactive. I noticed once I asked you to start asking questions, everyone did. Thank you. And that's good. Keep asking questions and pushing us. And we're here to kind of support you in doing stuff with UCoMP. So thank you very much. And that's all. So the next tutorial. So the next tutorial is by Mike Galloy, who's going to talk about data processing. There's going to be a break after Mike's talk. So I don't know if people need a quick break right now.
I need to move around so that they can fit a minute or two here.
Okay, so I'm going to stop sharing here. And just go around just for a couple of minutes and then come back. We'll have a full break at 10 o'clock.
I was going to sit back there. I was switching to and good to see you. Looking forward to it. Thanks. It's giving sense.